and thanks to the organisers for the kind invitation. Like Adam, my apologies to anyone who was at the meeting in Bonn, because I gave this talk there. But unlike Adam, I will not be speaking in Oxford, so perhaps an incentive for you all to go to Oxford. So I'm going to speak about a topic, joint moments, which builds on a lot of things that we've heard about so far. We've heard a great deal about moments in talks yesterday and today, and this will be a sort of conceptual extension of that, which I want to explain to you. So the motivation will come from number theory, as with most talks in this meeting. So just for the sake of completeness, I'm going to structure this by talking about the Riemann zeta function, although as I'll make clear, it's much more general than just the zeta function. So zeta is defined there for you as a Dirichlet series or an Euler product, and it has a functional equation, which you'll all be familiar with. And the key point is that it satisfies the Riemann hypothesis. So the zeros of the zeta function are meant to lie on the half line. Real part of Sn is 1/2. And so if we denote the zeros by a half plus I Tn, then these numbers Tn are all real. That's just a bit of notation for you. And the connection that really motivates what I want to speak about is this connection with random matrix theory. And I should emphasize most of what I say will be calculations in random matrix theory, but this slide explains why I'm doing the calculations. So the basic idea goes back to Hugh Montgomery. It's that the zeros Tn, the heights of the zeros up the half line, are meant to be distributed statistically like the eigenvalues of random matrices, and specifically either random unitary matrices or random complex emission matrices. And this was the observation made by Montgomery based on a theorem that he proved, and this has been built on by many, many authors, and I won't try and list everyone who's contributed. So one application of that philosophy, if you like, is that the value distribution of the Riemann zeta function on the half line, on the line where the Riemann hypothesis places the zeros, is meant to be like the characteristic polynomial of a random matrix. And again, many people have contributed to this story, and I won't repeat the whole history, although I'll say a little more later on just by way of background. And this story sort of connect the zeta function, zeros of the zeta function, connected to eigenvalues of random matrices, value distribution of the zeta function on the critical line being related to characteristic polynomial of random unitary matrices. This extends in ways that are now very well, at least very well sketched out. I don't think we have a complete understanding, but we have a quite a sophisticated understanding by now. This extends to other L functions, so it's not specific to the Riemann zeta function. We understand that L functions form families that are characterized by symmetry, and that various types of random matrices can appear in this story. These connections are, as I'm sure are well understood here, largely conjectural. They're based on, there are theorems that one can prove that are consistent with this picture, and lots of numerical evidence and lots of heuristics, but we're still far from a full rigorous understanding of these connections. But the sort of evidence in support of this is now pretty strong, and so this will be, I'm going to take this as read, if you like, and do lots of calculations in random matrix theory that, because of this, will, for reasons I'll explain, tell us about the Riemann zeta function and other L functions, things we might want to know. But just as a final point, and I won't emphasize this really was more the subject of Will's talk, we do understand now that for certain models of the Riemann zeta function, which are polynomials, that is, L functions defined over function fields, this all is a theorem in various different ways. So if you define your L functions over function fields related to a finite field of Q elements and let Q tend to infinity, Katz and Sarnak showed that you really do get random matrix theory describing the zeros and characteristic and the L functions. And recently there's been spectacular development in this subject, one that I find very interesting, which is that now this can be proved using really quite advanced ideas in topology for fixed large Q. You don't have to let Q tend to infinity. For sufficiently large Q, this is known to be true. So I want to give one example just by way of sort of historical context, which I think have been alluded to in several talks. And this concerns the moments of the Riemann zeta function. So these appeared in Adam's talk and in Will's talk, for example. So the moments of the Riemann zeta function are what you get if you take the zeta function on the critical line, take its absolute value, raise that to some power, and then average along the critical line. And these have been studied in the number theoretic context by many authors, going back to Hardy and Littlewood. Ingham made a significant contribution. So Hardy and Littlewood computed the second moment. That's when beta equals 1. Ingham computed the case when beta equals 2, the fourth moment. And many other people have developed this theory using essentially tools from number theory. But I want to think about this in a different way, and this is this connection with random matrix theory. And so the idea is if we want to understand the moments of the Riemann zeta function, and according to Montgomery's philosophy, you might expect the value distribution of the zeta function to be related to that of the characteristic polynomials of random unitary matrices. Let's look at the moments of those characteristic polynomials. So let A be an n by n unitary matrix. Denote its eigenvalues by e to the I theta n. These lie on the unit circle. And we'll denote the characteristic polynomial on the unit circle by p of A, depends on the matrix A, and theta, position on the unit circle. So here's that written as a determinant and written explicitly as a product over the eigenvalues of the matrix A. Then the moments in this case are what you get if you take the absolute value of the characteristic polynomial, raise that to some power 2 beta, and then average with respect to A in the unitary group, uniformly with respect to Haar measure on the group. So these are the moments that you would compute for random matrices, characteristic polynomials of random matrices. And the idea is to compare these moments with the moments of the Riemann zeta function, and hope that if we can compute in random matrix theory, this will tell us something about the zeta function moments according to the kind of Montgomery philosophy. But it turns out you can compute the moments of characteristic polynomials, and this is now a very old story, so I'll just go through this rather briefly in order to contrast with what I want to tell you later on. So this isn't the focus, this is just a sort of preamble, if you like. Anyway, I've got the moments of the characteristic polynomial. There they are, written again. And these are just the expectation value of this product of eigenvalues. And then you can compute the average over the unitary group using the Weyl integration formula. So you can write the moments as integrals with respect to all of the eigenvalues, theta 1 to theta n. And what appears is the characteristic polynomial, the thing you want to average, and then the measure on the eigenvalues, which is given by the square of the van der Monde determinant. And this integral you can compute. It's an integral that's exactly computable. This was done by Selberg in the early 1940s. It's a special case of an integral that he computed. And this is the answer. So here's an exact formula for the moments of the characteristic polynomials of random unitary matrices of dimension n. And you see that the formula is rather compact. It's a product of ratios of gamma functions. And there are a couple of things to remember about this formula. First of all, you can do this. This formula makes sense. The answer makes sense for complex values of beta. So beta doesn't have to be an integer. It can be a complex number, provided real part of beta is greater than minus a half. And it's an exact formula for finite, it's an exact formula. It's not an asymptotic formula. N here is a parameter, the size of the matrices. So we have this very simple formula for the moments. And this is going to be important that it is a simple formula, because I'm going to go to a case a little later where we wish we had such a simple formula, and I'll tell you the answer's more complicated. Anyway, given that simple formula, you can analyze it. So you can take the asymptotics, and you can show very straightforwardly that the moments grow like n to the power beta squared, and this is the coefficient that you get, the function, if you like, that makes that an asymptotic formula. It's a ratio of Barnes G functions. And if you do restrict to integer moments, so if we take beta to be k, an integer, the Barnes G function simplifies enormously, and you get this product of rational numbers. So m factorial over m plus k factorial, product from 0 to k minus 1. So you get this rational number appearing, and this rational number is understood to be, if you write it as gk over k squared factorial, then gk is an integer. That's a property of this formula. And this term gk has a very nice interpretation. So gk is an integer. It's the number of ways of filling a k by k array with the integers from 1 to k squared in such a way that the integers increase along every row and down every column. So if you like, it's the number of k by k Young tableau. So there's a nice interpretation. We've got an exact formula for the moments of characteristic polynomials. We can compute their asymptotics, and the asymptotics, certainly for the integer moments, has this connection to an interesting counting problem. And this connection to Young tableau was pointed out by Bump and Gambit in 2006. So the story for moments is very satisfying, and you can then use this and go back to this purported connection between random matrices and number theory. You can use this to make conjectures about the moments of the Riemann zeta function, and Will alluded to these in his talk. So for example, the 2β moment of the Riemann zeta function is conjectured to be, well, there's the random matrix part, this Barnes G function part, and then there's another part, an arithmetic part, which is expressible as an Euler product. And this is the term this term comes very naturally from the Euler product over primes. The blue term comes very naturally from the random matrix representation, the Hadamard product over the zeros. And if you use the hybrid formula, which Will spoke about at some length, then you pick up both terms. So the two terms kind of talk to each other in this way. At leading order, they factorize, but they don't factorize at all orders. So this is the structure just at leading order, that you have an arithmetic part coming from a product of prime numbers, and then a part here coming from the random matrix calculation. And that's the conjecture. And if you're interested in integer moments, k is an integer, then you get this rational number appearing again that's related to the number of Young tableau of dimension k. So the story is very complete, and we've understood this for a long time. So now I want to go to another case, which has been a puzzle for some time, and where there's been a lot of progress recently. So I'm now going to move to joint moments. I'll tell you what they are, and then explain to you a little bit about the fact that the story here is more complicated. So we're going to set capital theta to be this function written there in terms of the imaginary part of the log of the gamma function. And we'll define z of t, often called the Hardy z function, to be e to the I theta of t times zeta of a half plus it. And you do this because the functional equation for the Riemann zeta function guarantees that z is a real valued function when t is real. So this is just another way of saying the functional equation. This functional equation involved the gamma function, and that's why the gamma function appears there. So z of t is a real valued function when t is real, and it's the function that you often see plotted on those posters that come from Mathematica, where you see the sort of zeta function plotted. It's really z of t that's plotted. So the joint moments are defined as follows. They're what you get if you take the modulus of z and raise that to some power. Well, the modulus of z is just the modulus of zeta, because this term here has modulus 1. So if we stop there, these would just be the moments of the zeta function. But we're going to do something different. We're going to multiply by the absolute value of the derivative of z raised to a different power, and then average that along the critical line. So if you like, these are moments constructed so they give you joint information about both the values of z and the value of its derivative. And there are two, I've written this in a funny way for historical reasons, but there are really two parameters here. There's k and h. Basically, these are the two exponents on the absolute value of z and the absolute value of z prime. Now, we could have done this for zeta. The story is almost identical, but I'm doing it for z. It's a little easier to write some of the formulae. So these joint moments were introduced by Ingham in 1926, and they too have been studied in the number theory context by many authors. So there's a flurry of activity in the 1980s and 1990s, largely down to Brian Conry and his co-workers. And various cases of these were worked out, just as the moments were worked out. And just as for the moments, one might hope that there's some organizing mathematical principle that describes the joint moments, and that's going to be the subject of this talk. So an example of formula that Conry and Gosch worked out in 1989 was if you get the absolute value of z and multiply it by the absolute value of z prime and average that along the critical line, you get this very beautiful formula that involves e squared minus 5 over 4 pi. So these are not rational numbers now. And so the question is, what's the mathematical structure that underpins a coefficient like this, as opposed to the kind of coefficients that we saw for the moments, which seemed a little simpler? Well, that'll be the subject that I'll be speaking about, as I say. So obviously, we want to compare to the joint moments of characteristic polynomials. So we can construct something like the Hardy Z function, because characteristic polynomials of unitary matrices also satisfy a functional equation. You can also make them real on the unit circle. So you get the characteristic polynomial and multiply it by this function, which has modulus 1 on the unit circle. You get a function v, and v will be the analog of the Hardy Z function. And it's real valued when theta is real. And then the joint moments in random matrix theory will be the expectation value of the modulus of v raised to some power multiplied by the modulus of the derivative of v raised to a different power. And these joint moments make sense provided h is greater than -1/2 and k is greater than h -1/2. If you imagine k and h to be real, you can also extend this to the complex plane, but I'll think of these parameters as being real for the purposes of this talk. That's where these joint moments make sense, in that you avoid singularities coming from the zeros of the characteristic polynomial. So the question is, can we compute this expectation value? In the case when h is 0, we have these very simple formulae as products of gamma functions related to Young tableau. Is there an analog of those formulae when we stick in this derivative here? And the answer is, this turns out to be quite a complicated story. So the study of these in random matrix theory goes back to Chris Hughes in 2001, and many people have contributed to this subject, several of them in the audience here. And so I'm going to summarize the history by saying these seem intrinsically more complicated analytically. They're not expressible as products of gamma functions. They seem to have an intrinsically more complex mathematical structure, and it's that structure I want to describe to you. So going back to Hughes conjectured that for k greater than minus a half and h less than k plus a half, which is the range of the parameters where these moments make sense, that there is an asymptotic formula for the joint moments. So as n tends to infinity, these joint moments should grow like n to the power k squared plus 2h times some function of k and h, which makes this a sort of nice asymptotic expression. So that was his conjecture. And the question is, what is this function that would make this a nice asymptotic formula? So first of all, can you compute the joint moments exactly for finite n? Second, can you compute their asymptotics? And does it have this general form, the form I've shown here? And if so, what's the function f that appears in the leading order asymptotic term? So those are questions that we're going to answer in this talk. I should say that even for that establishing even the growth in n for general k and h was only achieved in the last year or two. So it's quite a difficult analytical problem. Perhaps there are easier proofs now, but the proof we have has turned out to be quite complicated. Now, why are you interested in this? Why would one want to go through all this work? Well, just as the moments of the characteristic polynomial tell you about the moments of the zeta function, we expect, and Hughes conjectured, that if you could work out what this function f was, that would be the thing that, from random matrix theory, that would be the function that appeared in the asymptotic formula for the joint moments of the Hardy Z function. So if you can do this random matrix calculation and compute f, you can immediately plug that in. You have the Euler product that appeared for the moments themselves, so that Euler product appears in both the moments and the joint moments. The question is, what is this function f that appears coming from random matrix theory that would be the right thing to put in for this formula, asymptotic formula for the joint moments of the Hardy Z function? So if we can do the random matrix calculation, we can immediately write down a conjecture. Hughes did this for the joint moments of Hardy Z. Yes?
If you put zeta prime instead of z prime, do you expect a different log power?
No, you get the same log power, but the lower order terms are different. And they're easy to compute. There's a sort of linear transformation between them.
So the arithmetic factor is independent of h?
Yes, it's independent of h. Yeah. So what do we know on the random matrix side? Well, Chris Hughes proved the scaling law with n for integer values of h and k, but he wasn't able to do it for non-integer values of h and k, and he wasn't able to get a really tractable formula for this function f. He was able to represent it as a limit of a sequence of determinants, but it wasn't clear that there was any, that was the simplest expression he obtained. So he showed that limit existed, but wasn't able to evaluate it in some simple form that one can analyze. Now you could take the approach that was developed by Bump and Gambit and plug in, use representation theory to try and do this calculation. That also turns out to be difficult. You get a sum of Young tableau, but they have complicated weights. It's not clear how to evaluate the sum in this case. It's not simply counting Young tableau. You have to sum over Young tableau with rather complicated weights. And that has proved to be difficult, although in certain cases it's feasible. In fact, Brian Wynne, in a very beautiful piece of work, in my opinion, evaluated using this approach, this kind of representation theoretic approach, this relation to Young tableau. He did the case when k is 1 and h is a half, which is the case that Conry and Gosch did on the number theory side, and he got from random matrix theory this constant e squared minus 5 over 4 pi. So that's rather satisfying. That suggests that random matrix theory tells you not just about the moments, but about the joint moments. And it stimulates you to think, well, can we do it in other cases other than this? But his approach got more and more difficult as K and H increased, and it wasn't easy to see a sort of organizing structure. For integer values of H and K, you can use this approach to recover the Hughes sort of result, the scaling with n. But again, this doesn't give you any simple formula for F. There is one case that was studied in some detail, and this goes back to work of Brian Connery, Mike Rubenstein, and Nina Snaith. That's the case when H equals K. So in this case, you're really just looking at the moments of the derivative. So these are, if you like, not the joint moments, they are the moments of purely of the derivative. And in this case, in random matrix theory, you've got an expression they obtained as a determinant of Bessel functions. And it was pointed out by Peter Forrester and Nick Whitty that determinant of Bessel functions satisfies a differential equation, one of the Penn-Levy equations. So that special case was very instrumental in, I think, people's thinking. The story has developed from there in ways that I'll now explain. So I'm going to tell you that in general, not just in the case when H equals K, there's a determinantal formula as well. And this was found by Brian Wynne. So Wynne, to set up the determinant, I have to tell you a few things. So Ln of alpha is a generalized Laguerre polynomial. I've written it here. That's its definition, either as a generating function or explicitly as a polynomial. K is this derivative of a Cauchy distribution. Then Wynne proved that the joint moments exactly, so no asymptotics here, n is still appearing in the formulae, the joint moments are exactly given as a certain limit of an integral involving this kernel K, which is just this very simple formula, and a determinant of these generalized Laguerre polynomials. And this is a Hankel determinant in that it only depends, the entries in the determinant only depend on the sum of the row index and the column index. So you have this expression that Wynne found, exact expression for the joint moments as an integral of a Hankel determinant involving these generalized Laguerre polynomials. So what I want to tell you, the story I want to tell you is that we now understand that determinant of Laguerre polynomials is exactly a solution of this differential equation. And this is what's called the sigma form of Penn-Levy 5. So it's a second order, nonlinear ordinary differential equation, and there it is. And you see the various parameters that I need. N is in there, sigma's in there. I'll tell you what all these terms are in a minute. But for those who haven't seen these before, and I think now increasingly people have seen this, but let me give you a brief reminder about what the Penn-Levy equations are, where they arise, because they become very important in mathematical physics over the last 30 or 40 years, and I think are increasingly seen as likely to be important in number theory. So let me go back to your first course of linear ODEs. There's a famous theorem that says that if you have a system of linear ODEs of this form, so W is the function we're trying to calculate, Z is the variable, the coefficients might depend on Z, but the system is linear. The solutions of this equation can only have singularities at points where the coefficients Cj are singular. So the solutions can't develop singularities at points where there are no singularities in the coefficients in the ODE. So this is now a sort of very famous result in ODEs. And another way of saying that is that the solutions of this equation can't have singularities that depend on the constants of integration. The singularities aren't movable. They're given to you by the equation. And so therefore, any singularities in the solutions don't depend on the constants of integration. So it's a well-known story then to try to generalize this to nonlinear ODEs. So it was known in the 19th century that nonlinear ODEs don't have this property, and they can have singularities that do depend on the constants of integration. And that's why nonlinear ODEs are one of many reasons why they can be much more difficult. If we restrict ourselves to singularities other than poles, so poles are easy to deal with. The singularities that are more difficult are branch points, because they affect the Riemann sheeted structure of the solutions of the ODE. And what you don't want is to be having to understand solutions of ODEs that live on some Riemann surface where the topology of the surface depends on the constants of integration. So the question is, are there any ODEs of this, nonlinear ODEs, which have no movable critical points, that is, no singularities other than poles, which depend on the constants of integration? And this was resolved for the first order nonlinear ODEs by Fuchs in 1884, who classified the nonlinear ODEs, first order ODEs, which have no movable critical points, no movable branch points. And they're these sort of Riccati equations that I've written here. And F has to take this form. So he proved that this was the sort of unique set which has this property. And we would now call these integrable. That's the modern sort of terminology for this. That wasn't the terminology then. Around 1900, Penlevet and Gambier showed that for second-order nonlinear ODEs, again, you can classify the ones which have no movable singularities, and there are, depending on precisely how you count them, around 50 of them. Numbers known precisely, but you've got to sometimes, there are different ways of counting them. But there is a precise, clear number of nonlinear, second-order nonlinear ODEs with the property that they have no movable critical points, that in the modern parlance are integrable. And of these 50, roughly 50, most of them had already appeared in the literature. They were expressible in terms of more elementary functions. But 6, it turned out, were sort of completely new. The solutions weren't expressible in terms of elementary analytic functions of the kind that had been studied before. And these are called the Penlevet equations, so there are 6 of them. And here's the simplest example. This is Penlevet 1. It's this equation here. So this equation is one of 6 second-order nonlinear ODEs that have the property that they're integrable in this sense, that they have no movable critical points. Penlevet 5 is this second-order nonlinear ODE. It's Penlevet 5 we're going to be interested in. So Penlevet 5, for those of you who know some integrable systems theory, Penlevet 5, the reason we call it integrable is you can express it in terms of a lax pair. So it's the consistency condition between these two functions. It's equivalent to this ODE here. And if you take this form of Penlevet 5 and make a change of variables, you get the formula that I showed you a couple of slides ago. You get the nonlinear ODE that I showed you before. So the one I showed you before is equivalent to this expression. So here's the theorem. And this was proved about 6 years ago now, 7 years ago. It's that the determinant of generalized Laguerre polynomials that appear in Wynn's formula, that determinant, you can write as a determinant of contour integrals. That's straightforward. That's just because the Laguerre polynomials you can write as contour integrals. So this is very straightforward with this weight. So this determinant of contour integrals that corresponds to the determinant of Laguerre polynomials, this exactly solves the equation I showed you before. This nonlinear ODE. It's a solution of one of the Penlevet equations. And so it's not expressible in terms of more elementary functions. In some sense, this is as simple as it gets. The solutions of this equation define new transcendental functions, and the one I showed you is one of those. That's perhaps why it's taken some time for the community to understand what the right structure is for these joint moments. They're not expressible as products of gamma functions. They're expressible in terms of solutions of Penlevet. So that's an exact formula. It's an exact statement for what the joint moments are for finite n. The joint moments at finite matrix size are exactly given by a solution of this equation with this asymptotic, this boundary condition, if you like, and that's as simple as it gets as far as we understand it. Proof, I won't go through the proof. I don't think this is the right audience to go through this, but I'll just say a few words. The idea is to formulate this as a Riemann-Hilbert problem, and we have experts in the audience on Riemann-Hilbert problems. So the idea is to express this in terms of a sort of higher dimensional complex analytic problem. That leads you to a series of ODEs. And these can be these ODEs that appear from expressing it as a Riemann-Hilbert problem. You make a series of transformations, and that simply reduces you to the lax pair for Penlevet 5. So you sort of do a lot of analysis, and Penlevet 5 jumps out, the lax pair of Penlevet 5. And then you simply have to determine which solution of Penlevet 5 is relevant for the particular Hankel determinant in question. And you do that by sort of matching particular cases, and then you have the solution that I expressed. So that's the idea. The idea is that the joint moments are more complex than the moments, and they're given intrinsically in terms of these solutions of Penlevet equations, Penlevet 5 in particular, for finite matrix size.
Sorry, H doesn't appear in
Yes, it does. Yeah,
It does?
yeah, it does. This might seem very abstract. And what use is it? Well, it turns out you can solve these Penlevet equations very straightforwardly using, you can find recurrence relations for the solutions. And so this does allow you to evaluate the joint moments very effectively. It's a computationally very effective approach. So if we denote Fn0 as this ratio of Barnes G functions, then you can compute as many joint moments as you like via a recurrence relation, simply by substituting in a series solution into the Penlevet equation and using that to relate the coefficients. That gives you a recurrence relation between the coefficients, and then you can find formulae for the joint moments by solving the Penlevet equation. So this is actually a very computationally effective approach. Those formulae I just showed you, if you take the limit as n tends to infinity, they do indeed, the terms grow like n to the power k squared plus 2h, which is what Chris Hughes had conjectured. And you get these expressions, very explicit expressions for the function f, which is defined to be the limit of the joint moments divided by n to the power k squared plus 2h. So this is a way of getting very explicit formulae out if you want them. So that what I said applies for finite matrix size. It's an exact formula, exact representation of the joint moments in terms of solutions of Penlevet 5. But what about the asymptotics? What if we are interested in the large matrix asymptotics? Is there a general statement you can make? Well, yes, because you can just simply do the asymptotics of the solutions of Penlevet equation by letting n grow and scaling appropriately. So that allows you to prove the following theorem, which is that the joint moments do grow like Chris Hughes conjectured, and this function f that appears in the asymptotics, the thing that we've been after, because that's what's going to be applied to get conjectures for the joint moments of the Hardy Z function. This function f you can write explicitly in terms of the Barnes G function, and derivatives of the exponential of the integral of a function here, which is a solution of this nonlinear ODE, second order ODE. And this is the third Penlevet equation. So exactly joint moments are given in terms of solutions of Penlevet 5, but the asymptotics reduces to solving Penlevet 3, which is a different Penlevet equation. It's the one I've written here. And that just follows from an analysis of some Penlevet asymptotics analysis. And this formula, which we got proved here from the exact formula for finite n, it turns out was also obtained simultaneously by Emma Bailey, who's here, and other authors, Brian Conbury, who's here, at the same time, using a very different approach. So there's not just one way of skinning this cat. I've told you one way, but there are other ways. And so you can get the asymptotics in multiple ways, either from the exact formula or going directly to the asymptotics. And that's what Bailey and co did. So those formulae are very effective for the integer joint moments. What about the non-integer joint moments? Well, here the story is quite interesting, I think, and has been a little complicated. So you might ask, can we establish in some general way the scaling, the asymptotics that Hughes conjectured for non-integer exponents in the joint moments? And this actually was more difficult. You can't get it directly from Penlevet, as far as we're aware. Perhaps somebody who has more expertise in that subject would be able to do this, but we weren't able to do that. However, we were able to get it in a different way. So let me explain about the asymptotics of the non-integer joint moments, which I remind you, for the moments themselves, this was very straightforward. This is simply going from factorials to the gamma function. Here, this seems to be more difficult. So let Wn be the Weyl chamber, so set of points which are ordered in this way. And we'll define a probability measure, which is sometimes called the Hoare-Pickrell measure. It's a measure Mn on the Weyl chamber, and it's defined in the following way. So here's the measure. We take these points, which are ordered in this way. We form this product of what looks like a Cauchy distribution on the points. And then we put in the Vandermonde factor, square of the Vandermonde factor for differences between the points. So that, did I do something wrong? Ah, okay, here we go. We're back. Let's get this show back on the road. So we have I'm switching gear here a little. What I'm saying now doesn't connect logically with what I've said before. I'm going to make the connection. I've simply defined a space of points, and I've defined a measure on that space. And then you can ask if points distributed according to that measure have an average value. So if I sum all the points and normalize by the number of points I've summed over, does this converge to a random variable? And this is a very interesting question, actually. It turns out to have appeared in many areas of probability and analysis. So it was studied by Vershik and Olshansky, Borodin and Olshansky, Chu. There's a whole sort of, and it turns out that they do. You can prove that the points distributed according to the measure I wrote down, the Hoare-Pickrell measure, do converge to a random variable. And this random variable that appears, xs, I'm not going to write explicitly, but it's appeared in many other places in analysis. So one example, it appeared first of all in the work of Vershik in classifying ergodic measures on the space of infinite dimensional Hermitian matrices under the action of infinite dimensional unitary matrices. So this random variable appears very naturally in this classification of ergodic measures on the space of infinite dimensional matrices. So what's the connection? Well, the connection is that what we were able to prove a couple of years ago with Theo Asiotis and John Warren is that if you get the joint moments, now for I'm not restricting to integer exponents in the joint moments, integer variables. For any variables in the full range where the joint moments are defined, the joint moments, you take your joint moment, you divide by n to the power s squared plus 2h, which is what Chris Hughes conjectured. You take the limit as n tends to infinity. What we can prove is that that limit does exist and is non-zero, and it's simply related to the expectation value of moments of the random variable x of s, the random variable that appears from the Hoare-Pickrell measure. So that finally proves the conjecture that Hughes made for the full range of variables, but it seems to be a more complicated story than certainly for the moments themselves. So that's one thing we've been able to do recently is to understand the asymptotics of the joint moments in terms of this Hoare-Pickrell measure and in terms of this random variable x of s, which is defined in terms of that measure, but which appears in other places in very interesting ways. So it seems to be a sort of rather interesting universal, semi-universal distribution that appears in many interesting problems recently. And I want to switch to a different question, which is, so far I defined the joint moments in terms of absolute values of the characteristic polynomial and their derivative. What if you have higher derivatives in there? So what if, in random matrix theory, what if I'm interested in a product, expectation value of a product of absolute values of arbitrary derivatives of the characteristic polynomial, symmetrized, to arbitrary powers? So what I told you, the story so far, was simply the case when I've got a product of two terms. One of them involves the zeroth derivative, and the second involves the first derivative. Now I'm asking, does that mathematical structure I described generalize to arbitrary derivatives and arbitrary combinations of derivatives in this way? And this was actually a question that came from number theory. So Roger Heath Brown asked me this about 5 or 6 years ago, because for the Riemann zeta function, these combinations of higher derivatives are really quite important. And I won't say precisely why, but there are various reasons why derivatives of the Riemann zeta function or the Hardy Z function are very interesting. And so understanding this more general structure was something that Roger wanted me to do. And for a long time, I was rather pessimistic because you can write these as determinants, just as we had for the joint moments. In that case, they were Hankel determinants. In this case, as soon as you have higher derivatives than the first, the determinants are no longer Hankel. And so I was actually rather skeptical that you would get relations to Penn-Levy equations. And I thought that maybe some more complicated story would unfold. But it turns out I was wrong. And in fact, in general, expressions like this are related to linear combinations of solutions of Penn-Levy equations. So the start of this was work with Fei Wei, who was my postdoc in Oxford. This is something we did a couple of years ago. We were able to show an asymptotic formula for these generalized joint moments that involve arbitrary derivatives and arbitrary powers of derivatives, we were able to show that these were expressible as a sum involving derivatives of solutions of Penlevet 3. And the sort of idea that was required was that even though the determinants that appear are not Hankel determinants, you can think of them as Hankel determinants, in a sense, convolved with Young diagrams, so that you can think of them as shifted Hankel determinants, and you have to sum over lots of these Hankel determinants, but each of them is really a Hankel determinant where the sort of Hankel restriction, that the matrix elements only depend on I plus j, you get additional terms coming in, and you can think of that as summing over Young diagrams associated with Hankel determinants. And when we realized that, we were able to show that this general case, just as for the joint moments we considered before, these now are expressible in terms of these sum of derivatives of solutions of Penlevet 3. And we were able to get explicit formulae, just as we got for the joint moments, the sort of elementary joint moments. You can get explicit formulae then by solving these nonlinear ODEs, these sum of derivatives of Penlevet 3. You can solve that by substituting in series and getting recurrence relations. And so just as for the elementary joint moments, you get rational functions appearing as n tends to infinity. And the structure is actually rather similar. More recently, with Theo Asiotis and Alpagunas and Fei Wei, we've been able to show that this is true not just asymptotically, but exactly. So we were able to show that these generalized joint moments are all expressible exactly in terms of sums involving derivatives of solutions of Penlevet 5, and then recover this formula by looking at the asymptotics of Penlevet 5. So we now have two different approaches to getting the asymptotics. You either go directly for the asymptotics, or you go to the exact solution and then analyze the asymptotics of the exact solution, and both give the same answer. And again, in the exact case, you get rational functions appearing, so a very similar structure. And just as I did with Theo Asiotis and John Warren, you can ask, what are these joint moments have non-integer exponents here, non-integer powers? Well, again, there's a connection to, if you like, a generalization of the Hoare-Picquerel measure, which allows you to prove, sort of in a very general form, asymptotics of this kind of expression for the non-integer powers. And it's again related to random variables that are like generalizations of the random variable x of s that I defined earlier. And then very recently, just a sort of month or so ago, we managed to extend this. Everything I've said so far has been for the unitary group. Well, the same story, it turns out, holds for the orthogonal and symplectic groups. Again, it's always exact solutions in terms of Penlevet 5, asymptotics in terms of Penlevet 3, and that seems to be a sort of universal structure that appears for all of the classical compact groups. And this is relevant. In fact, there have been some number theory papers on L functions that have symmetry other than of orthogonal and symplectic types. And the question arose there whether there are extensions of Penlevet that would describe those, and so we were able to answer that question. So we now have a pretty complete understanding of these joint moments, I would say, in terms of solutions of Penlevet equations. So I'll finish with a question, which for me is the really burning one. It's not the formulae that I showed you, which I personally happen to like, but you may not. For me, the interesting question is, so on the number theory side, you can compute moments. You don't have to use random matrix theory at all. You can use kind of number theoretic techniques of classical number theoretic techniques involving correlations of the divisor function, etc. This is exactly how Hardy and Littlewood Ingham and others approached the problem. So you can use purely number theoretic approaches to compute these joint moments, and people have done that in special cases. And the formula that Brian Conry and Amit Ghosh derived was an example of that. But so you could compute more cases in principle. But without knowing what the answer's meant to look like, it doesn't really give you a structure to approach. Well, now we have the answer in the back of the book. The answer in the back of the book is that these joint moments that one calculates using number theoretic techniques should be related to solutions of Penn-Levy equations. And for non-integer moments should be related to this very curious random variable x of s, which describes the average value of the set of points distributed according to the Poiseuille-Pickrel measure. And my question is a general one, which is a sort of conceptual one, if you like, which is, can you go directly from the number theory to integrable ODEs, Penn-Levy equations, without computing case by case? Is there some general sort of way, at least heuristically, to see that the joint moments in number theory should be related to the theory of integrable ODEs and should be related to this random variable x of s, which I say has very interesting incarnations in ergodic theory? And I don't know the answer to that. I think it'd be wonderful for people to think about it. I certainly am thinking about it, but I would hope other people would be inspired to do so as well. But for me, this connection with integrable ODEs and the theory of the zeta function, it's not the formulae that matter, it's the connection that matters. And it's that connection I wanted to tell you about today. Thank you.
Thank you very much, John, for a great talk. Any question, Matrice?
Yeah, no, you've seen an essential point, which is the reason you write these powers historically as 2h minus 2s and 2s or what have you, is because the logarithmic derivative is actually the simpler thing to go for. And so you really want to separate this out in terms of moments of the characteristic polynomial and the logarithmic derivative, and that's where the structure's simpler. And I do believe what you say is correct, that this random variable x of s is most naturally interpreted in that way. So I agree with you.
Other questions? Emma?
So to do that, you'd have to do something which I haven't done, but Brian and Nina Snaith and co-workers have done, which is to look at the joint moments off the unit circle. So if you're interested in negative moments, you first have to go off the circle, form your negative moment, and then take the limit as you approach the circle. And I think it's possible to do that according to this approach, but we haven't done it. And it may be it's more difficult than I thought, but I believe it is possible, but we haven't done it. Brian and Nina and co certainly have explored that in certain special cases. You get exactly. It's basically the sum of all the powers that appear. So it's n to the power k squared minus twice the sum of all the powers that appear. Yeah.
So it's all linear.
Exactly so. Yes. So in that limit, which is a very kind of confluent limit, Penn-Levy, you're absolutely right. Penn-Levy reduces to simply the product of factorials that we know is the answer for different reasons. So that's one thing that we proved. It
becomes like an algebraic solution.
Exactly so.
Penn-Levy equation for
Exactly.
some parameter.
Exactly so. Exactly so.
No more questions? Thank you very much, John.